Okay, so I'm going to be talking about some traits that futures give you and a subtle pitfall that I encountered at my work. So I work at a company called Hadean. We use Rust heavily there. So let's say you want to get a bunch of data from machine 1 to machine 2. It's a load of structs. So let's say you've got 1 million of these. They're about 2 megabytes in size, maybe. How are you going to move them? The first answer is probably going to be something synchronous. So you convert your structures to bytes using SERDE serialization, and Bing code is a decent one here. So hands up for anyone who's heard of Bing code? Okay, so most people in the room. So it's, for people who haven't heard of it, think of JSON, but it's not human readable at all. It's just a way of turning something that you write in Rust into something you can send over the wire. You then need to frame those bytes. What that means is you count how many bytes your serialized structure is taking up, and then you add a length in front of it. And this means when you're receiving at the other end, you receive the length, allocate a buffer, and then put all the bytes into that. And then you can send that over a TCP stream. So if you look at the complete end-to-end of this process, you start off with your set of structures over here on the left. You serialize them in each one in turn. You get the length of them and you send the length prefix, and then you send the actual data. On the other end, you read your length, read the data, deserialize it, and you get your structures back. Pretty straightforward. Nothing much unexpected there. And in this case, we're using a TCP stream to send between machines. But we want to be able to do other things at the same time. So we might want to be able to do other I/O, reading and writing from files, sending to other machines, etc. We have more to do than just send to a single other machine. And so what we can do, there is a module in the Tokyo util crate, Tokyo util codec, that does the framing for us. So who's used Tokyo framing before? Tokyo framing, Tokyo SERDE? Okay, so far fewer people. This is something that when you start, if you want to do serialization and async at the same time, this is probably where you want to go. And so you combine Tokyo util codec with Tokyo SERDE, and that's the part that handles the actual serialization. So what this ends up looking like, I'll gloss over the top bit for a second. So the writing part is you get your asynchronous writer, you create a future which just loops from 0 to 1 million, and you send the data and await it. Okay, so it just does that. And on the other end, you're doing the same in, but receiving it. There was a question earlier about streams. So the reader is actually a stream, so an async iterator of these structures. This is a bit of noise around actually how to construct the appropriate type to make sure that you can send these structures over the wire in an asynchronous way. So you're using a Tokyo SERDE framed with a framed writer and all of like using Bing code. So it's a little noisy, which is a bit unfortunate, and finding actually usable examples of this can be tricky the first time you come to it, but that's approximately what it looks like. So a little aside, so there was an excellent talk earlier on that's kind of set me up very nicely to cover this slide. So I don't have to go into much detail at all, actually. So the futures crate provides a number of key pieces of the ecosystem. So futures combinators, a number of traits like async reading, async writing, like streams. Tokyo, by contrast, is best known for being a runtime. So you can take your futures, give it to Tokyo, and away it goes in order to run them to completion. But Tokyo also provides a number of its own traits and key pieces of the ecosystem. And unfortunately, these aren't always compatible. So there was, I think there was a mention earlier of a fragmented ecosystem. This is a perfect example of it. And what I'm going to do is dive quite deep into this to see actually how I was seeing a 5 times slowdown in a bit of code because of some of this incompatibility. So let's take the async read trait. So if you've ever read something in Rust from a file or something like that, you'll be familiar with the std IO read trait, where you pass in a mutable slice of U8, so much more like this one. You pass in your buffer, and it will fill up the buffer. So futures on the left-hand side also takes a slice of U8. But Tokyo has decided to use something a little bit different, a read buff struct. So you can't use these two traits interchangeably. You can ignore the pull read vectored because it's not relevant here. So what's the difference? Both of these traits take an output reference where they're going to actually put the data. One of them's a slice of U8, one of them's a read buff. In the slice of U8, the bytes have got to be initialized. So who put up your hands if you're aware of the difference between initialized and uninitialized memory and the implications that has on undefined behavior? Okay, so maybe about half the room. So just to go into a little bit of detail on that, when you ask for memory from the operating system, it comes back to you as being allocated, but it's uninitialized. What that means is you're not allowed to read from it. If you read from it, generally, it's allowed to do anything. So your computer may blow up. This is the origin of the famous quote in C about demons flying out of your nose. If you read data that has been allocated but not initialized, horrible things will happen. So the futures trait says, hey, you've got to have the bytes initialized, but then I'm actually going to write over them anyway. Tokyo reasonably went, well, this seems a bit silly. Why are we initializing some data that we're going to write over as we read the data? So that it uses a read buff. So that allows parts of the buffer to be uninitialized. And so this is a difference between calloc. So if you're familiar with C, calloc will allocate uninitialized memory, whereas malloc will just allocate the memory. Fortunately, so we've got these two traits, we can't use them interchangeably. Fortunately, there is a type that Tokyo gives you. It's Tokyo util compat. So this type here. And this just provides a compatibility layer so that if you have a futures IO, a type that implements the futures IO async read, you can use Tokyo IO async read. So it's useful for converting backwards and forwards between the two traits, so that if you have a section of code that uses one of them, you can then use the compat struct and pass it to a section of code that uses the other. It's very useful for trying to deal with the fractured ecosystem that was mentioned earlier. So just a reminder, you've already seen this code. We actually use this here. So you can see that in the writer, we're passing a type that implements the futures IO async write. But the framed write requires something that implements the Tokyo version. And so we have to use this compat write function, which wraps it in this compat struct. So, okay, we're wrapping loads of things in another structure in order to do a conversion. That doesn't seem too bad. So we've got this futures IO async read, wrap it in compat. That allows us to use the Tokyo IO async read trait. Great. So a single read call now looks like, so hands up who's looked behind the scenes of how futures get implemented, particularly regarding poll. Who's seen a poll implementation? Okay, so maybe about a third of the room. So behind the scenes, the way that futures work is a runtime will say, hey, can you do some reading? And the futures implementation will come back and say, all right, I did a bit, but I'm not completed. And sometime later, the runtime will go, hey, can you do a bit more reading? I've done a bit more, not completed, etc. That's the general flow. So poll read gets called, which says, hey, compat struct, can you do a bit of reading? Because we've passed it a read buff, which may have some uninitialized memory, we then have to initialize the memory. So that makes it usable. Because it's then initialized, we can then convert it via a mutable slice of bytes. So we can then pass it to a futures IO async read. So it's just about converting between these two traits. This is the actual implementation. So there's not much there. So we take in this read buff, we initialize the buffer itself, and then we pass it as a slice just here. So there's not a huge amount going on here. But there is something wrong. Does anyone have any guesses about what might be causing performance problems here? We've got some guesses.
So some data gets converted and then it returns and says there's nothing to do anyway.
Not quite, but there is unnecessary work that may be happening. So almost.
Yeah, I think it's initializing the entire buffer every single time instead of just what it's reading.
Spot on. So the problem is that every time you pass in a read buff, it has to initialize the whole thing. So every read call will try and initialize the unfilled part of the buffer. This is actually potentially fine, right? So the way that a read buff, this is the official documentation on how a read buff is structured. You've got the capacity, so that's how big it is in total, the amount of memory allocated. You've got the filled part, that's data that's usable, and you've got the unfilled part. That's stuff that's arbitrary. You can't use that. The other tracking is what's initialized. So you might have more initialized than filled. So if you've filled part of your buffer and then read some of it, then all of that stuff that you've read, that you've taken back out of the buffer is still initialized. It's just not useful to you anymore. So you also track initialized and uninitialized. And that's how this is broken down. So when you do initialization, you can move this pointer all the way up here to the end and say, hey, my whole buffer is initialized. The problem is that when you're using framed read, remember we're using a framed reader in order to read out the structs from the wire. The frame reader passes a structure called bytes mute and also uses buff mute internally. This does not track initialization. It only tracks filled and unfilled. So every time the receiving end of your framed reader wants to perform a read, the compat wrapper struct has to reinitialize the data. Okay, setting memory is kind of quick. It can't be that bad, right? No big deal. Well, I was seeing a 5-time slowdown. So so we had a bunch of compat calls in order to do these wrapper structs. I was seeing a 5-time slowdown in production code at Hadean. And the cause of this was we had large structures. So Tokyo would optimistically use large buffers, thinking, hey, maybe we can get some large reads, fill it all up at once. Large reads are more efficient. But you have small network reads. So you're doing lots of initializations of large buffers. And so you've got a lot of initializations. I then kind of reduced this to verify that this was a problem. This shows a 2-time slowdown. So you can go and like download this, run this yourself. And this simulates a network, it throttles reads, it uses an in-memory pipe. And you can see that there's a 2-time slowdown. In slow mode, it takes about 15 seconds, fast mode, about 9 seconds. So the way that you can potentially fix this is at Hadean, we actually like removed all our compats. So we moved to purely using the Tokyo traits. In this repository, it shows the minimal change that you can make. So this is the original code. So we've got this framed read using compat with length delimited and the bin code. All we do is we add a Tokyo IO buff reader right here. So wrapping around the compat struct. And what that does, all that's doing is it ensures that initialization is tracked. It makes sure that we're not reinitializing a bunch of memory every single time. That's it. And that's the way that it shows the 2-times improvement. The final possible fix is that Tokyo fixes it directly. So this has been a known bug for a while. There's been no activity on it. It would unfortunately require them to break backwards compatibility. So I don't know. Closing thoughts. Try to, in this fractured ecosystem of async Rust, try and buy into one part of it. So either Tokyo or futures. If you can't do that, sometimes it's not possible. Be really careful when you're using framed reading and writing, and consider using this buff reader trick. So the repository is available online, so you can read it yourself to see how it's done. Very easy. It's about 5 seconds to make the fix, and you'd see significant improvements. Another important takeaway is to have an intuition about how fast you think something should go before you run it. Because the only way that I discovered this was I was looking at the transfer rate and I was just thinking, this is far too slow. How is this possible that we're transferring at 10 megabytes a second? This is ridiculous. We're in the same data center. And so I looked into it and eventually discovered this kind of initialization problem. Fast operations can be slow if you do it too often. And you can get leaky abstractions, even in Rust. This is a leaky abstraction around buffer management. That's it. So here are some links that may be of interest. And that's the end. Any questions?
Thank you very much, Aidan. Please give him a big hand. Any questions? All right, I'm going to pass. Okay, yeah.
Thanks a lot for your talk. Would you suggest if somebody were to make a library, author a library, and they wanted to expose an async, a function, how do they stop from just, having millions of features to support Tokyo and futures? And is there what's the best way forward? Some madness.
It's a good question. I think, so personally, my default would be to go for the futures crate. So start
futures core.
Well, the network of futures crates. So futures core, futures IO, etc. That's my personal bias. So I'm a member of the Rust core team, Rust infrastructure team. I bias towards things that are closer to the Rust core, and I think those are. But on the flip side, Tokyo is the runtime, and if you're using Tokyo as a runtime, it may make more sense to do that. I personally would tend to bias towards the futures ecosystem where possible.
Thanks.
So is there a canonical runtime that people use when they use the futures ecosystem then?
There is no canonical runtime. I think the most popular one is Tokyo. Unfortunately.
So kind of hard to avoid using both.
Yeah. This is as I think the talk earlier outlined, this is a bit of an ugly corner of the Rust ecosystem. I thought the pitch for having a default executor in the standard library makes sense, but I don't think it'll happen. Yeah, it's a bit of a shameful corner at the moment. It's kind of tricky. I'm not gonna lie. Question?
Yeah, when you said you were initializing memory, like what's it actually doing? Is it just sort of writing a bunch of zeros and saying, here you go with a nice clean buffer, or is like what was so slow about it, or is it just that you were doing it an incredible amount of times? Or
yeah, it's just because it gets done so often, right? So it's just doing a mem set, so writing zeros to memory. That's it. Like you'd expect that to be really, really fast. Turns out that even that can be slow, if you do it often enough. Yeah.
You mentioned that the futures and the Tokyo ones have different traits, have different signatures, and that the standard library read trait is similar to the futures trait, which has the performance problem that you have to initialize the memory.
Yeah.
So it suggests that the standard library trait is also suboptimal.
Yeah. So I'm a little bit dubious about the performance speed ups implied by not initializing memory, to be honest. I think that in practice, like my unfounded belief, not based on any kind of professional opinion on building things with lots of buffers and whatever, but my personal belief is that if you're going to be reading and writing using buffers, you're probably going to have buffer reuse. You're not going to be allocating them every time because, I mean, even just like using a malloc and then writing to that suddenly in Linux at least, may force the kernel to actually do the allocation. So Linux may choose not to do allocations the first time you ask for memory. So you actually probably just want to reuse something that's already been used. At that point, if you amortize the cost of initialization once, I'm a little skeptical. I mean, if you're really going for that level of performance, yeah, you need to potentially allow for initialized buffers. But I think the simplicity of the I stand behind the standard library traits, to be honest.
I mean, yeah, I was going to comment.
Well, open question.
Just behind you, if you want to pass the mic behind to the gentleman on the corner.
I think it's already been passed to
Oh,
someone.
okay. Sorry. And then you'll be next. I know you want to ask a question as well.
Yep. You've been describing the problem that the memory allocation have been happening too often. Is there any other way how, because for different tasks that can be, the overhead cannot be, that doesn't have to be like that big. Are you able to like change the size of the chunk you are actually processing to mitigate that from a different point of like?
Yeah, so it's not so much to be clear, it's not the memory allocation, it's the memory initialization.
Right.
So it's that we're mem setting every time. So as I think I mentioned here, so the core problem here was we were using large structures and the network reads were relatively small. So let's say the structures were, I can't remember, let's say 5 meg in size, and the network reads were, a few K. So you could bypass this problem or make it less obvious if you have smaller structures, because you're probably only going to be reading one at a time. So that's one way you could mitigate it in your data layout. But in practice, you'd probably just insert the buff reader, in which case you have that single buffer that you're reusing every single time that tracks initialization. So that's probably the recommended way that, if I understood your question correctly, the buff reader is the way that I'd recommend to sidestep this unfortunate interaction between compat and the async read traits.
Just one last thing.
Yeah.
Is it possible to actually like enlarge the network frame so to be closer to your chunk?
So in this case, it's well, maybe it might be, it might well be possible. I think yes. So when in this code, so I talk about it simulates throttling. So I think it limits it to like 32K reads at a time or something like that. If you can receive a megabyte each read call, it's probably fine, because the thing that's taking time is going to be actually, I'm not sure it would help. It would help a bit, but there are two problems here. The total amount of memory that you're zeroing out, that's the fundamental thing. And so if you're getting sizes of data transferred that's closer to your buffer size, you have far fewer of that. So it would help, but it wouldn't completely solve the problem, because ideally you just don't want to initialize each time.
And last question here.
Huh? I have a fancy mic. So one thing that I'm quite curious about at the moment is the sort of IO U-ring stuff that's popping up in Linux. Is there any plans in the sort of the futures IO ecosystem to take advantage of that and start having like async syscalls?
That went in an interesting direction. So you're not specifically asking about IO U-ring in the context of IO. You're asking about the more general question of IO U-ring for asynchronous syscalls.
I think that, well, if you've got one, why not have the other?
Yeah. So there's been a bunch of work and experimentation around IO U-ring and how that interacts with the Rust ownership model, which is non-trivial. I think there is some integration somewhere. Like there are a few crates that have experimented with this. There are some crates that are trying to integrate it into async executors. I mean, I'd expect Tokyo to be one of the first ones to be able to leverage IO U-ring, but that doesn't. I'm not convinced that answers your question about just general asynchronous syscalls. I think asynchronous because for those unaware, so IO U-ring is a relatively new syscall in Linux that allows you to give some give a block of data to the kernel, then satisfies the request, it puts it onto a queue, and it goes through this queue. And there are different ways of configuring IOU ring, like dedicating a CPU core to just busy looping on IO requests from IOU ring. And so one can imagine a Rust configuration where you say, hey, start up my IOU ring thread. Your executor now operates entirely within the kernel. Your IO executor operates entirely within the kernel. And then your asynchronous calls are just like calling a single syscall and then waiting for it to come back. So you don't actually have a Tokyo thread of control executing separately. So you're not using a multi-threaded executor anymore, using a single-threaded executor where the kernel does the multi-threading. So there's interesting possibilities. I think there's going to be a lot of design space here for interesting patterns and ways to represent that in Rust. I think it's going to be a few years before we actually see the spectrum of possibilities.
Thank you very much, Aidan. Big hand for Aidan. And where can we find you, Aidan? How can we bug you more about things? So anything you want to plug as well, please feel free to go ahead.
This is my username on GitHub, on Twitter, on basically anything. So you can find me in all of these places. I'm also on the Rustlang Zulip, which is a place where Rust people hang out if you're interested. Also on the Rustlang Discord. I mean, if you're interested in meeting other Rust people, I encourage you to join the Rustlang Discord and Rustlang Zulip, because they're welcoming. You can find things that are of interest to you. There are lots of interesting projects going on at all times in the Rust ecosystem. Yeah, everyone starts somewhere. I started by fixing issues in CI on Rust, believe it or not. So yeah, there's a place for everyone.
Absolutely, absolutely. A big hand for Aidan again. And we are going to be wrapping up now. We're going to head to the pub, the usual pub, the Harlequin, which is right by the Sadler Wells Theatre. So you're welcome to join. There are still some bits of swag here.